Hello students, myself Amrita Dhar, Assistant Professor of Electrical Engineering Department of Greater Kolkata College of Engineering and Management, JIS Group.
In this video, I will discuss about dielectric heating. This topic is included in Module 2 of the subject Utilization of Electric Power. Subject code is EE702. In this video, I will discuss about dielectric heating. When a ferromagnetic material is subjected to alternating magnetic field, it gets heated up due to eddy currents induced in the material and the hysteresis loss in the material. The hysteresis loss is due to reversal of magnetic field, which brings about magnetic molecular friction and results in heating the material. Similarly, when an insulating material is subjected to an alternating electric field, the atom gets stressed and due to the interatomic friction, heat is produced, and this is known as dielectric loss. Okay. Now, we know that an atom of any material consists of nucleus, positively charged at the center, and electrons, negatively charged, surrounding the nucleus. The center of the negative charge coincides with the nucleus and hence atom as a whole acts as a neutral particle. Now I just draw a picture. So this is neutral atom and this is polarized atom. Okay, now when this is subjected to an electric field, the charge distribution is distributed and center of the negatively charged does not coincide with the nucleus and the two centers are displaced by a distance. Okay. Now in this figure you can see that two charged are displaced. The electric is said to be polarized, and if the charge on the nucleus by say nucleus is Q, the product QD is known as the dipole moment. Okay, the product QD is known as dipole moment. The forces it acts in direction from negative charge to positive charge. If the electric field is alternating, the forces within the atom are reversed and a distortion of electron path occurs in the opposite direction. The atoms are thus in a constant state of unrest, changing with each shift in polarity. It is observed that the loss increases a constant state of unrest changing with each shift in polarity. It is observed that the loss increases with increase in frequency and strength of the electric field. However, if the electric field applied is very strong, it may overstress the charges and hence some electrons may be knocked off from the outermost orbit and resulting in rupture of the dielectric medium. Also, as far as possible, no air gap should be left over between the electrode and the specimen to be heated, as normally the dielectric strength of air is smaller than those of dielectric materials to be heated. Also, for any voltage applied across electrodes, the electric field intensity in the air gap is higher than in the specimen. Now, if an air gap is left, the air will be ionized and may result in breakdown. Therefore, it is desirable in dielectric heating not to apply high voltage but to use high frequencies. Even though voltages up to 20 kV has been used, but from personnel safety point of view, voltages between 600 to 3000 are more common. Now, all dielectric materials can be considered to be imperfect capacitor and can be represented by parallel combination of resistor and capacitor. I just draw the diagram so you can understand better. So here IL through the equivalent resistor, the leakage current resistor, and IC represents the leakage current. This is IC. IC represents the leakage charging current of dielectric. And dielectric loss P is equals to V square by R. So from the phasor diagram, it is clear that V by R by V omega C is equals to tan delta. So V by R is equals to V omega C tan delta. Therefore, P is equals to V square omega C tan delta. Now, if delta is very small, then delta is equals to tan delta. So, we can write this is equals to V square omega C delta. Okay, this is equals to dielectric loss, where delta is in radian, is known as loss angle. And it is an indication of the state of dielectric, whatever it is, healthy or unhealthy. Higher the value of delta, less healthy in the state of dielectric material. Okay, so delta is the loss angle. Now, capacitance of a parallel plate is given by, you all know that this formula. That is C is equals to epsilon 0 epsilon R A by D, where epsilon 0 is the permittivity constant, epsilon R is the relative permittivity of the medium, A is the area of the plate, and D is the thickness of the medium in meters. So therefore P is equals to V square 2 pi F epsilon 0 epsilon R A delta by D. So P is proportional to V square and P is proportional to F. The product of epsilon R and delta is known as loss factor. Epsilon R into delta, this term is known as loss factor. Now whereas the relative permittivity epsilon R is the indication of retained energy due to molecular deformation, whereas delta is an indication of the amount of leakage current which will flow through the insulator and so produced a heat loss. Therefore, there are limitations on the use of extremely high frequency for dielectric heating. For maximum power transfer, the output impedance of the source of frequency must be equal the impedance of the inter-electrode, which keeps on changing with change in frequency. The impedance of the workpiece also changes with the change in mass of the same material or different materials having the same mass. There is a fixed frequency for a particular workpiece when for a particular voltage the power transfer can be maximum. It is practically not possible to have different generators for different workpiece. Therefore, additional units of electrical capacitance or inductance must be used either in series or in parallel or in a combination of both with the workpiece in order to match the impedance of the load with that of the generator. Okay. In general, as mass of the workpiece increases, the optimum frequency decreases. Another reason why certain frequencies are better suited for a workpiece of a given dimension is the formation of standing waves. Now, if the distance between electrodes equals quarter or half wavelength at a given frequency, standing waves would be set up along the electrodes. Just I draw the picture so you can understand better. And voltage would be maximum at one point and 0 at the other point. Okay. As a result, the dielectric material will not be uniformly heated, and therefore it is important to choose a suitable frequency of supply so that standing waves are not formed. A safer and judicious solution will be to select a frequency such that there is a great difference between the electrode spacing and the quarter or half wavelengths. If it is not possible because of conditions imposed either by the load or the source, some other means like introduction of tuning stubs must be provided to avoid formation of standing waves. Yet another reason why very high frequency should not be used is the difficulty of constructing a tuning circuit inductance to resonate with the capacitance of the charge at such high frequencies. For frequencies higher than say 40 MHz, the value of inductance required is only a fraction of a microhenry, which may be difficult to realize in practice. And taking all these factors into account, it has been observed to use frequency in the range of 10 to 40 MHz. Now, what are the applications of dielectric heating? The fact that water heats at a much more rapid rate than any other material when subjected to high frequency field, dielectric heating is most conveniently used for moisture removal, especially when the moisture is disposed uniformly deep into the material and no conventional method can be used for its removal. And it is also used for heating thin films such as lacquers and paints applied to metallic surface. The preparation of thermoplastic resins, heat sealing of plastic sheets, bonding of laminated wood, drying of textiles, dehydration of food and tobacco, sterilization of cereals, preparation of chocolates, popcorn and many other applications. However, it is to be noted that cost of the equipment is quite high and this method should be employed where other methods are impractical or slow. Next, we solve a problem. Now, a slab of material 2 cm thick and 15 square centimeter in area having relative permittivity 4 and power factor of 0.04 is to be heated using dielectric heating. The power required is 200 watt and a frequency of 30 megahertz. Determine the voltage required and the current that will flow through the material. If the voltage were to be limited to 600 volt, what should be frequency for the same power requirement? Okay. So, capacitance C, the value of epsilon 0 is 8.854 into 10 to the power minus. So, at first I just write down the formula. C is equals to epsilon 0 epsilon r A by D. Okay. Now, the value of C is 8.854 into 10 to the power minus 12 into 4 into 150 into 10 to the power minus 4, because we have to convert it into square meter and D is given 2 centimeter, so we convert it into meter. So, final expression is 26.56 picofarad. Okay. Now, capacitive reactance, that is XC, is 10 to the power 12 by 2 pi 30 into 10 to the power 6 into 26.56. That is equals to J 199.84 ohm. Okay. Now, cos phi is given 0.004 and from this we calculate tan phi, which is equals to 24.98. Now, V omega C by V by R, we all know this is equals to tan phi, which is equals to omega C R. Now, 1 by omega C is equals to 199.84 because capacitive reactance is given, is calculated 199.84. So, from now 1 by omega C is 199.84. This is the capacitive reactance. We have just calculated it. So, the value of R is equals to 24.98 by omega C, because tan phi is 24.98. So, 24.98 by omega C is equals to R and the value of R is 4992 ohm. Therefore, V square by R is equals to 200. V is equals to root over 200 into 4992. This is equal to 999.2 volts, which is almost equal to 1000 volt. Now current IL is given by 1000 by 4992. The value of R is 4992. So IL is equals to V by R, that is equals to 0.2 ampere. And IC is equals to V by XC, and this is equals to 1000 by 199.84 ampere. Okay, so this is the IL 0.2 and this is IC 5 ampere. So total current total current 0.2 square plus 5 square 5 ampere. Now if the voltage were to be limited to 600 volt, then R is equal to 600 into 600 by 200, that is 1800 ohms, and omega CR is equals to tan phi equals to 24.98. Omega into 26.56 into 10 to the minus 12 into 1800 is equal to 24.98. I just put the value of C and R. Okay, C and R. So omega is equals to 522, and from here frequency is equals to 522 by 6.28. That is because omega is equals to 1 by 2 pi f. The pi is 3.14, so 3.14 into 2 is 6.28. So from here f is omega by 6.28. So frequency is 83.12 megahertz. This is the solution.
That's all from today's class. If you have any problem, please contact with me. My contact details is given on the first slide. Thank you.